gonna give up. All right. Okay. Wonderful. All right. Well, welcome to session 1 of this Here Type Check deep dive series. This is kind of a continuation of these, what are they, Rustc Explore things that I was doing back when that was a thing, but that kind of lost steam. And but I really liked giving these little recorded lectures and having them be uploaded to the YouTube channel. So this is somewhat unstructured though, because I have no idea what people actually want to know, and two, kind of how deep we should go. So I'm going to try to keep it light, or not light, but general this time around. I'm going to start kind of just giving a high level introduction of like what Here Type Check is, like what its purpose is and stuff like that. And then maybe get into the weeds of how types are passed around in Here Type Check and how expectations work and stuff like that. Ultimately, then kind of setting the stage for more in-depth deep dives in the subsequent weeks. I'm not sure if I'm going to make this like semi-weekly, like every other week or every week or whatever. I'll probably be opening up for feedback when this lecture ends, just to see when, like, what people want time-wise. I know some people can't join because of the time zones and stuff like that, but you know, unfortunately, Rust is a global project, so it's not going to work for everyone unless I wake up at like 6 a.m. So, all right. Well, so Here Type Check is the process of checking function bodies and other things that have bodies. So I'm going to open up my test file that I always use. So for example, like, you know, checking the function body of f in main, checking the const, a const body is the same thing. Anything that has like a part of the item that needs inference done inside of it. So Here Type Check is the process of checking any type expectations that come from the signature. So for example, f in main returns the unit. We need to actually make sure that f in main returns the unit, and also inferring all the other types inside of f in main. For example, if I, you know, did let x's defaults and then return x, we need to both determine that x has the type unit, and that type unit comes because we try to unify it with the return type of f in main. So when we return x, we set it like equal to unit, and that causes us to be able to determine what the self type of this default type is. Because if you'll know UFCS, this is actually just sugar for this syntax. So default is a trait, it's not a self tie. So we need to find out what the self type of the function is. All right. Here Type Check is organized around a context called fn context. Fn context is kind of a misnomer. It's used to type check anything with bodies, as I said before. Consts, for example, are not functions, but they have bodies. Statics are not functions, but they have bodies. Closures aren't really functions, they're functions inside of functions, but they also use fn context to check their body. It wraps the more general inference context called infer context, and it adds a little bit more contextual information that is used very heavily when we're doing function type checking. So within a given item, there's a param, which is all the assumptions that we can make about what types are implemented for what, or what traits are implemented for what types inside the body. So we pair a param, and with it we pair, when a function returns a tie, we pair something called a coerce many, which is used to kind of take all the ties in every single return statement inside of a body. and squish them into one type. If it's a generator, we store the yield and return tie or resume ties, and just a bunch of other contextual information that's used heavily when type checking something specifically something with a body. This actually wraps another kind of intermediate context thing called inherited. So inherited is used to share type information between an outermost body and the inner bodies of things that are type checked alongside with it. So this is, as far as I'm aware, just closures and possibly anonymous constants. So constants inside of things like type description, when you have like a type description for an array tie. Actually, that might not be true. I think closures, anonymous closures, like closure, open bracket, close bracket, are checked like, or anonymous consts, sorry, my bad. So something like this. Pretty sure that anonymous consts share the same type checking context as the closure, or as the item that contains it, because we need to have inference types flow between them. So an inherited actually is the thing that wraps the inference context that I said earlier, but it also stores the type check results for all the bodies together. And a fulfillment context, which is used to process trait goals. Any questions right now before I continue? Nope. All right. So inside the inherited, we also defer a bunch of checks, like casts happen at the end of type checking. Just this is more of an implementation detail than something that y'all need to know for like a deep understanding about how type checking works. So but we don't really ever use the inherited directly. It's just every function context wraps an inherited, and there may be multiple function contexts, one for every closure, for example, inside of a function, that all wrap the same inherited. And that's how they all kind of inherit the same inference context, the same trait engine for checking trait stuff. But yeah, so let's see. So the main entry point into the type checking of an item is called check. I think it's called check FN. Yes. So this check FN is the thing that we use to check functions. It takes a function context and it takes all the information that we know about the function, which is its signature and its body. And it basically does the kind of the top level expectation, which is basically that the function returns, that the body of a function evaluates to a tie that is equal to the return type of the function. So as we will see, type checking is kind of a recursive process where we pass in expectations about ties. So we say, for example, in an if statement, we say that let cont, or if cont, we pass in expectations. So like, for example, cont always, there's no case when cont is ever not a Boolean. So we pass in the expectation that cont is a Boolean, and we check the type of cont, and we make sure that the type of cont is a Boolean afterwards. So that is, we basically pass in the expectation that cont is a bool, and then outwards, like out, we get cont is some tie, and we check that tie is bool. So this is generally in programming language parlance called bidirectional type checking. So it's, as in types both flow into type check expressions, or sorry, type check functions, and also types flow out of type check expressions. This is somewhere in the middle of kind of an implementation of type checking and also kind of the theory of type checking. And Rust obviously doesn't implement, bidirectional type checking from a paper. It implements its own type checking algorithm that is inspired by bidirectional type checking. But I think y'all will see very soon why, like kind of how this works in practice. I think this is a little bit too high level to actually understand exactly what it means in practice. So right. So type checking begins by taking a body. In this case, we're really only going to be talking about functions because type checking things like consts and statics are really easy. We take the return tie. I'm going to skip over how we deal with opaque ties or return position infiltrates in function signatures, but we just, just be aware that that's something that does happen. And maybe I'll go into more detail about opaque types in a future lecture. We take the return type, we stick it into this thing called a coarse many, which is used to kind of smush together a bunch of different types at different points in a program. So it's used for things like matches. It's used for things like if, else, like then else, the two branches from a then else, we need to kind of smush their types together, in a way that's not just equating those types in the case that, for example, we have two different closures in the return type. We can coerce them into function pointers if they capture nothing. So like this, like this is valid code. Or let's see, so coerce many is a thing that helps us kind of deal with things when we have possibly multiple arms. And you can think of a function body with a bunch of different return statements everywhere, and also just like the final return of the block as kind of like an expression with a bunch of different arms, where each one of the arms is a return statement, and then there's a final arm, which is like the last expression in the body. So, and then skipping over some generator stuff and skipping over where we initialize all the locals in the body, which is essentially just we walk through the body, and if we see a local, we compute its type and store it into a table that is useful for accessing later. Then we check all the patterns of the inputs, which I'm also going to skip over for now, because I want to get to the interesting part, which is check return expr. So check return expr is basically like the entry point for checking the body of the function. So we can jump into it, and here's kind of the most important part, which is check expr with hint. So return expr is a bit of a misnomer. This probably should be renamed, because this isn't checking a return expression. This is checking the body of the whole thing. So you can think of a function main, or let's come up with something that returns something more interesting. 32 returns 1. You can think of this whole return body as kind of just like a top level return expression. You can think of it kind of like this. So that's how we type check it. We type check. We pass in the whole block that is the body of the function, and we pass it into a check return expr. And we get into kind of the meat of this lecture, which is this function, which is check expr with hint. So it takes an expression in here, and we can pass it in something called the hint, or the expected tie, which is the return tie. So in the case that we have this test function, we would be checking this block here with the hint that the return tie of this block should be an I32. And that allows us to propagate a tie into the type checking of this block, which possibly allows us to kind of know that we're type checking that this literal 1 is an I32 sooner than if we were to check this block without a hint. Out from the type checking process would proceed, and out of the type checking process we would get an int variable. So type variables there's different flavors of type variables. One of the type variable flavors is just int kinds. Whenever we have a literal like 1, we don't know what kind of 1 it is yet. And we later on then would be inferring that that type variable 1 for the literal 1 is an I32. And this is kind of an inefficient process. This is an inefficient process because we know that the return tie of the function is I32. We don't have to wait until the function is done type checking to kind of unify that fact with the thing that we get from type checking the body. And also it leads to better diagnostics because we kind of have more type information sooner. And so, yeah, so this is kind of what I was trying to get at when I said that it's kind of in the middle. So bidirectional type checking is kind of in the middle of an implementation concern and also the theory, because it means that we have more eager type information in different places. But it's also just, it means that we compute things sooner. So it's both more efficient and also possibly leads to better type checking results, both on the good path and the bad path. I'll pause here just for a second before we jump into all these different check expert functions. Does anyone have any questions? Let me open up the chat and see if anyone. Nope. Give it a second. Alrighty. Well, if people do have questions, send them in the chat or something like that, or just speak up. I don't really care. So we take the whole body of the function and we check it with the hint that that body should evaluate to what we pass in with the return tie. So what does check expert with hint actually do? So check expert with hint is just a kind of a nice wrapper around check expert with expectation. It takes this more kind of interesting and diverse enum called expectation that it basically allows us to specify how binding our expectation is. So expect has type means that we expect that the expression that we're type checking and the type that we eventually get out of that exactly has the type that we pass in with it. There are different types of expectations though that are, again, different levels of binding, and that we then are only able to take advantage of to different extents. So expect R value, like unsized, for example, is used for type checking things that coerce into slices. So for example, if I wrote something like this, this is a slice of I32 equals this, we would like to be able to use the fact that this slice is an I32 slice to eagerly infer that these 1, 2, 3 literals are I32 literals. They're not U32 literals. They're not U size. However, we cannot use the fact that this variable is assigned the type, which is a slice of I32, to infer the type of this whole expression, because if y'all don't know, the type of this expression specifically is not an I32 slice, it's an I32 array of, length 3. So if we were to take this I32 expectation and kind of impose it onto this array literal, several things would go bad depending on how you implement it. If you implemented it in the kind of the hard way, which is to unify this I32 type 3 with the slice tie, we would just say that we have a type mismatch. If we use it in kind of a more of a type inferencey way, we might get an expression, or we might get an error that says that we can't take an address of something that's unsized. So what I'm trying to say is essentially expectations are sometimes they have to be treated a little bit more weakly than just the expression should have the exact tie that we passed in. Sometimes we can only take advantage of, for example, expect R value like unsized will be used to only infer the return type, or sorry, the element type of a slice or an array. Same thing with expect castable to type. Expect castable to type is used when we have, x equals some expression as pi. So expression, when we have some cast expression like this, we don't want to impose the fact that tie, or that expr has the same exact tie as tie, but we can bubble up some of the information that we learn from that into expr for unsizing purposes. Like if we're saying that this is a box of din something, then we can propagate that in to this expression in order to help unsizing in certain ways. Right. Any questions about that? No. Okay. Alrighty. So luckily though, check X for hint is very simple. It just passes in the plain type expectation. It recurses into check expr with types, and or check expr with expectation and args, which is something that takes an args array. We see this pattern a lot in the compiler where a simple function wraps something that has more arguments, that wraps another one that has more arguments, and we basically just keep bubbling down more and more type information until we get to the bottom, which is just the thing that takes advantage of all that. So check expr with expectation and args is used only in cases where we're type checking something that is callable on the left-hand side. If it's not callable, then we don't use those args at all. And we just don't ever take advantage of that information. So check expr with expectation and args is basically the big humongous type checking function where we match on all the different expert kinds. So essentially, we have an expectation that's passed in. We want to evaluate the type of the expression that we pass in. So we jump into check expr with kind, unless it's a path expression. Again, this is the thing I was talking about with paths are the thing that we use to represent the callable kind of something that is callable. So when you have a function like whatever, this is represented as a path. And if we had an arg here, like 1i32, we can use this to infer the turbofish arguments of drop eagerly. However, if it's not a path, then we can't use anything eagerly. So we just jump into the check expert kind, which is the big humongous match that we use to match on all the different type kinds or expert kinds in here type check. And depending on what the expert kind is, we pass in the expectation, or we sometimes don't because the expectation can't be used. Hello, I'm back. Someone like Santiago, can you confirm that you can hear me?
Yes.
Okay.
Yes.
I hope that didn't, I hope everyone didn't drop. And I hope this recording is still working. Anyways, I don't know where I got dropped off, but as I was saying, we, depending on what the actual expression that we're type checking is, sometimes we can't use expectation. So Yeah, so sometimes we can't use that expectation and we just don't even pass it in. However, sometimes we can use expectation, and let me see. I don't know if there are any good examples of things that use expectations. Oh, I guess check X with closure is, I'll begin kind of getting into check X with closure. I wanted to do a whole lecture on checking closure kinds. But I'll at least begin to clean it. So for example, we have a function like this. Let X is fnw8 equals X, anything with it. When we're type checking this let expression, we take the described tie of the let expression and we pass it in as an expectation to the right hand side. So we type check this closure expression with an expectation. As we can see, check X for closure actually does take an expectation. So we believe that it gets used, and we can see right below that it does get used. Expected.toOption. So toOption is essentially just one of the ways of matching on an expectation. All it does is it just matches all these different expectation kinds. And if it's anything that has a tie, it'll return it. So this is essentially like, give me the weakest tie expectation that you can give me. I don't care if it's just that you can unsize into that tie. I don't mind. I just want any type of expectation. So if we do have an expectation, then we can use that tie expectation to deduce the closure signature. Deduce closure signature, I'm not going to actually go into it, but essentially you give it a type in, and then it will try to extract the closure signature out of it. So if it's a function pointer, it will try to extract the signature from that function pointer. If it's a din fn once, for example, then it will try to extract a function signature from that. And if we get one back, then that's great. We can then check the closure using that expected signature. And if we don't, then too bad. And that's sometimes why you'll get, like, for example, you will get a, let's make this into a string so I can do something fun to it. Or it can be a U8. I think you'll get a type error if you try something like this. We'll see. I don't know off the top of my head what creates all these. No, that is too good because we have toString as a, we need an inherent, oh, right. So this code works. If we take away the expectation, then we don't know what X is. And I don't think that yes. So what happens is, within this closure signature, we don't know what the type of X is unless because we remove this type description. And that means that we don't know what the receiver tied to this toString function is, and we bail with ambiguity. So that is kind of how expectations are propagated in for great good, because being able to eagerly infer that this return tie is U8 means that we then now have enough type information to be able to proceed in cases where we wouldn't if we didn't pass in these type expectations into expressions. Any questions right now?
I do have like a question for like an earlier point of yours.
Okay.
You said like the return expression is checked with the expectation of hash type, not coercible or something. But like if you, for example, have a function which returns a reference to a slice, but the actual return expression is an array or like a reference to an array, it still works out. But what's the reason? If the expectation is hash type.
Yeah. Yes, that's a good example.
Something it shouldn't
I can write it out. I'll write it out and we can talk about it because this has to do with two things. One is the way that the expectation is used by this thing called coerce many, and two is the way that expectations are weakened as they get passed into sub-expressions. So let's see, U8, and then we passed in like, yeah, U8 slice, like 1, 2, 3. This should type check if I give it an
You have to tick static.
Oh, right. Yes. Yeah. Yeah, so that works. And you're right. You're right. This kind of goes against what I literally just said as my motivating example, which is when we try to check with the expectation of has tie, it should try to impose that this tie, the type of this expression is literally the same tie as the thing that we passed in. And that has to do, I think it has to do with the fact that we use this machinery called coarse many in the, where were we? Jump back into check expert return, I think, or check return expert. Yes. So the fact is that we grab the tie out of this ret coercion, which is the thing that's used to kind of find the lower bound between all the ties that we return in all the return statements and stuff like that. And I mean, I guess we could just jump through it. So we check expert with hint, we check expert with expectation, go into args, we jump into kind, we check expert, what's it, adder of, I think is what we call yes, check expert adder of. Right. So we check, so then we take the expectation that we pass in to this adder of expectation. We call only has type, which is again another one of those like matching functions that, but unlike the two option one that we were using before, this one only returns something if we have just expected has tie. So this is the strongest expectation that we have in the kind of the orderings. Where were we? So we match on that. If we have a tie, then we match on that tie kind. If it's a ref, then if it's a ref, then we ignore the fact that I don't care about syntactic place expressions because we are not taking mutable pointers to things. We then take the tie that's being matched on, or the pointy tie of the ref, and we pass it back into expectation R value hint. And R value hint is the thing that weakens the expectation when it's a slice. So the thing is, so we pass a slice tie into R value hint, and instead of creating another expect has tie with just the slice, it gets like downgraded into expect R value like unsized when it's the slice. So what happens here is that we basically, expect that it has the same, this is like is tie of U8, but then when we type check just the array 1, 2, 3 is R value like U8. Does that make sense?
It does, yeah. Like so it's special case basically.
Yeah. So that's what happens all around type checking. Expectations get passed in, and as those expectations are like unwrapped and stuff like that, they get weakened in certain places. Same thing with unsized expectations. You can see it here with dynamic, but when we're in a match block, we drop certain types of expectations in order to make certain useful expressions pass and stuff like that. It's a little ad hoc. Trying to change this stuff does sometimes cause weird errors. It's unsatisfying sometimes, but that's how it works. Is that it starts out as kind of an expect has tie expectation, and it gets weakened and when we pass into this helper called R value hint. So right. And the way it justifies is because this R value hint isn't being used for type safety. It's not being used for correctness purposes, just kind of used for best effort inference behavior. One of the things is that the only problems that you can ever have when you get the wrong expectation is that the is that unsizing and diagnostics are messed up. The thing with bidirectional type checking is that we always check that the type that we get back is of the right type. So we're never going to have we're never going to have type safety problems in your type check. We only would ever have sometimes code goes from passing to failing because we are missing type information or something like that. So yeah.
One question. So expectations, like, are they never gonna have inference variables in them?
They do. And there are some cases where we, like right here, adjust for branch, or we throw away the expectation if it has an inference variable. So for example, this is used when we're trying to find the lower bound of two closures. So I think I gave this example earlier where we have, I should make a name, where sometimes we have, if true, doesn't matter, we have two closures that both take U8s and they return nothing, for example. So these are two distinct closures. Oh, no. These are two distinct closures, but because they capture nothing, they can be coerced into both. They can both be coerced into function pointers, and just given the way. So let's see if this works. Yes, so it does work. I wasn't lying. And given the way that expectations get propagated into if statements, if this adjusts for branches, so adjust for branches is used for things like checking the then else for an if statement. So for example, this, let's call it infer number 0. This expectation of expr has tie gets passed up into this check then else with the infer of 0. But then whenever we take that expectation and we adjust it for both of the arms of the if statement, we throw away any expectations that are equal to a tie var. And that's because we don't want to infer that this tie var is equal to some closure or tie closure, whatever, because then when we check the other arm of this if statement, we say this is a different closure tie than the one that we inferred from the then arm. So that is how it works, is adjust for branches will sometimes match on tie vars and we'll throw them away. So I guess to answer your original question, expectations have tie vars. Expectations can have tie vars even if we just write tie vars in code, like if I wrote like this, or like the expectation will have a tie var right there.
Right.
Any more questions?
It's always gonna get thrown away, right? Like the expectation.
Can you
in
repeat
case
that?
they have like inference variables in them.
So it's only when the expectation's equal to a tie var, like exactly.
Yeah, I see. Okay. Yeah.
And this is just to handle the case where we don't know what the return, what the expectation is, for the that case that I was giving with the two closures that need to be, we would want to propagate it up. Like we would want to propagate the fact that this closure has to have the tie of fn u8 up to the thing. So that's why we only throw away the expectations that are equal to tie vars specifically, instead of like just checking the closures with no expectation at all. So yeah. Any more questions before I move on? Thanks for those questions. They were really, really useful. All right. So I don't know where to go on from here. Other than, so we check the return. So going all the way back to where we started, we check the expression, of the body with the hint of the return tie that we can kind of infer from the signature. And this check expectation, we don't do any unification here. So as I said before, we need to actually then just like double check that the type that we get back from this is actually equal to the tie that we expect it to be. And where does that happen? Return ties are weird because we don't have any like we don't really have we have the signature to type check it against. Let me find a better example. Let's go into check expert. Let's see, check expert. Is that? Nope, that's the wrong. Let's check. Let's see. Where do you check the expression for declaration? Check decal initializer. Yes. Okay. Right. Okay. So I don't know what to go into detail because I wanted to cover these later in their own sessions, but and also everything is like spaghetti in here type check, so I don't know how to jump over things without making it confusing. Anyways, I guess we could just kind of jump through some of these different check expert functions. So yeah, as I said before, there are different types of expectations, and there's a bunch of helper functions that kind of wrap these expectations. There's one which is like check expert has type, which then checks expert with expectation, wrapping it up with this expect has type. We don't necessarily need this function other than the fact that then every call site, which is there's probably like 50. Oh no, actually there's only 8. Would have to wrap their expectations with expect has type. It does also turn out that we have a special case where check expert has type is not exactly true. It's check expert has unless that type is never. And if that type is never, then it's fine. So this is used specifically for the case like the main return, then this is fine. So the check then else function, which is the way that we check if statements, checks the condition, which is here, checks that the condition has the type bool, but we know that the type never is not, it's not in like the programming language, like PL theory sense. It's not the subtype of all types. It can be coerced into every type, and we allow specifically just that coercion for things, even if we have the hard expectation that a tie has, for example, or that an expert has a tie bool, for example. And so that's kind of the special case that's being implemented right here. So as if the tie is never, we allow that never tie. We store something called an adjustment, which tells us later on that when we're generating MIR, we need to unsize it kind of from a never tie into something else. So once we check that tie, or once we check the expression with the expectation that we pass in, we then need to like double check that the thing that we got back actually is equal to the thing that we expect it to be. We do that here with demand soup type. So demand soup type checks that the expected tie is a super type of the actual tie that we got out of type checking. And it's prefixed with diag because it gives us the diagnostic back, because we want to be able to pin on a bunch of useful type mismatch suggestions, like, oh, did you mean to call .toString before storing it into a string variable, and all these other things. But we just get the diagnostic back and we extend it in different ways, and we emit it afterwards. There is also just the regular demand soup type, which does nothing but call demand soup type diag and then emit it right afterwards. There's also the similar functions like check expr coercible to type, which also takes a type expectation in, but instead of using soup type, like super typing, it uses coercion, which I'm not going to cover, I don't think, today, because I wanted to cover in a different lecture, as I said before, because that one is just a whole can of worms. It uses a bunch of machinery to try all the different types of coercion, because coercion, unlike super typing and subtyping, is kind of a best effort approach, because we're literally just taking two types that are not related to each other, and we have a bunch of different hard-coded rules of how to turn them into each other depending on how much type information we have. But similarly, some positions in the code, we don't really care that the types are equal or that they're super types, subtypes. We just care that we're able to coerce one type into another. So this happens in struct constructors, for example, and even in let statements. Let statements can coerce their ties into the expectation that you have on. So like box of display, for example, box one. So if this was a hard type expectation, then this dim display would be propagated up into the return type of this box new, and we would say that we can't call the box new constructor on something that's unsized. And also we would get a type mismatch because one is not equal to the type display. All we care about is that the thing that we get back from this let expression is coercible into the thing that we assign here. And that's only if we have a actual type hint to coerce it into, like type description on a let statement. Any questions? Or anything that y'all want me to go into more detail about? Because we're 52 minutes in, so I could wrap it up, but I could also keep talking. Nope. All right. Let me double check if there's anything else that I didn't cover. So again, that's the general structure of type checking, is that we start from the function body, we have the signature of the function body, and we basically propagate down the expectations from that function body into sub-expressions. Those sub-expressions then bubble up the ties that they get inferred to be, and then we make sure that those types are either equal depending on the expression, or coercible, depending on the type of expression we're checking. And hopefully through that process, all the type variables and all the type information that we need gets inferred through the program. Different expressions do different things with the expectations that they are propagated, like that get propagated into them, depending on kind of the semantics of the expression. That those semantics, as I demonstrated before with all these different helper functions on expectation, are sometimes kind of special, and they represent a lot of different special cases that we want to work in Rust. If you're writing a programming language yourself, you might not want to settle on these semantics, but those are the semantics we have because we want people's code to work in certain ways. Sometimes we have pretty fluent expressions that would otherwise break if we didn't have these kind of backwards compatible hacks. And I'm hesitant to call them hacks because they do lead to kind of nice code. It's just that the only way of checking them is by having kind of more and more complicated fractal-like type checking code. And that's why that all lives in here type check. Anyways, thanks for attending lecture number 1. Hopefully next time I'll be a little bit more kind of nitty gritty in the details now that you all have kind of a high level understanding of the structure of your type check. I think I'm going to be going into either closure type checking or coercion next time. I'll have to figure out which one I have more to talk about. Both of those have pretty complicated algorithms that we can step through, and I'll have a lot of different example programs that I want to demonstrate how they work. So those will possibly be more interesting lectures. Thanks for listening. And I think we can stop the recording. I don't know if Santiago gave me the right to stop the recording.